Hello my dear warriors, welcome to the Vedantu English channel, and this is your Captain Shreyas. And first time on YouTube, you're going to see this concept of experimental physics for the very first time on YouTube. So there were some experiments which were added in 2024, right, from your competitive exam point of view, and I feel that we should do these experiments separately because I know many coaching institutes, just one second, yeah, many coaching institutes won't deal with this. Many people end up skipping this, but let me tell you, I'm going to cover up all these experiments which were added recently. And also let me tell you, you might get at least one question. Reason being, since it is mentioned explicitly in the syllabus, right? So I feel there will be at least one question, and maybe if you are lucky or unlucky, you might get two questions from this. So let me know, my dear warriors, if I'm audible and visible, right? Let me know in the chat box. All right, at least I can see myself over here. Yes, I am. Good evening. Now I have mentioned the weightage just now, right? The weightage will be at least 4 marks to 8 marks, maximum 2 questions, minimum 1 question. And I feel these questions are going to be very straightforward. There will be some data given and there will be some formula which will be used or some concept which is applied, and based on that you have to find the required thing. All these things are usually taught as a theory part when the specific chapter is done, okay, when a specific chapter is done. But many times it happens there are some additional things in these experiments which needs to be tackled separately. So I'm going to go through all the experiments, number 1. Number 2, I'll show you the formula or application or the concept behind it. Number 3, I will show you some questions also based on it. So are you ready, my dear warriors? And if you're ready, put some hearts, put some smileys in the chat box right away, right now. Yes, this is going to be a long class, let me tell you. This will definitely be a very long class, definitely. Okay, happy evening. So let's begin with the lecture, and let other students also know that Shreyas sir is live right now on the channel, so that they also do not miss this particular lecture. Okay, let's start. My name is Captain Shreyas, in case you do not know about me, and I have been teaching kids for a very long time, producing awesome amazing results and sending kids to the top-notch institutes in the country. And here I am to make sure that today you study really well so that tomorrow you enter your dream college. So thank you for liking and thank you for subscribing the Vedantu English channel. Wow, nice to see all the hearts coming up. Very good. So everybody is active. Awesome. Thank you so much, dear students. Thank you so much, means a lot. Now the first experiment is vernier caliper. See, in this particular experiment, generally what happens, you will be given certain values regarding what is the main scale reading, vernier scale reading, and then you will be asked to find out what is the least count, what is the diameter, what is the thickness, those kind of things. What is the job of a vernier caliper? The job of a vernier caliper is to measure basically the dimension of length, like for example, to measure the thickness of a book, to measure the thickness of a sheet, to measure the diameter of a wire, to measure thickness of some nail. So those are the applications of vernier caliper. In a vernier caliper you have the jaws. In the jaw you keep the object. Maybe I can put one pandu over here, and what is the thickness of this pandu? So you clamp those jaws, and when those jaws touch the object you cannot move it further, and that's when, looking at these values, you will be able to figure out the actual width of that thing. Yes, in this vernier caliper you can see this particular thing. This is your basically your main scale, you can call it. This is your main scale. This particular part is basically your main scale, my dear warriors. And do you see this one over here? This can be slided left and right. that is called as the vernier scale. What is it called? It is called as the vernier scale. So this is called as your vernier scale, and this one over here is called as your main scale. Keep that in mind. Main scale, keep that in mind, right? If you put a pandu here, you can measure what is the width of this pandu, but here on the top, you can measure the internal diameter of some object. Imagine there is a hollow cylinder, some thick hollow cylinder. So if you put the cylinder over those jaws you keep on expanding till it touches the inner parts of that cylinder. You can measure the inner diameter. So imagine this was a hollow cylinder like this. This is the thickness. So you can measure this value from the internal jaws. Here you measure the outside diameter or outside distance or outside length. So this is used for inside length, this is used for outside length. That is the main application of a vernier caliper. Till this point everything is clear? Till this point, my dear warriors, is everything clear? Do let me know in the chat box. Great. Now very good. Now, how do you measure the least count? How do you measure the reading? How do you measure the diameter and all these things? Let's have a look at it. First of all, what will be given to you is you will be given the number of divisions of vernier scale coinciding with the main scale divisions. Just using this data, and also the length of one main scale division will also be given to you. Just using these two data points, what you can find is basically the least count. What you can find is basically the least count of the vernier caliper, and the formula for finding out the least count is the smallest distance that can be measured. This is nothing but your smallest distance that can be measured, can be found, and that least count is the modulus, meaning I don't know which one is bigger, which one is smaller, but the modulus of one main scale division minus one vernier scale division. One main scale division minus one vernier scale division. Example, let me give it to you over here. If 11 divisions of main scale coincide with 10 divisions of vernier scale, then the least count is how much? LC means least count. Then the least count is how much? Let's have a look at it. And what should be given? One more thing, it's a normal scale. So for a normal scale, one division of the main scale is always 1 millimeter, unless it is given otherwise. One division of the main scale is 1 millimeter unless it is given otherwise. Okay, so now this much is given. Question is find the least count. What you will do is, my dear students, the least count will be nothing but, observe this very carefully. One division of main scale minus one division of vernier scale. One division of main scale minus one division of vernier scale. So one division of main scale minus one division of vernier scale. One division of main scale is already given. The main scale which is there are some divisions on it. One division on that main scale is already given to be 1 millimeter. Is that right, everybody? Great. In that, what is the length of one vernier scale division? So for that, use this information. 11 divisions of main scale is 10 divisions of vernier scale, meaning 11 millimeters corresponds to 10 divisions of your vernier scale. 10 divisions vernier scale will be 11 millimeters because each division is 1 millimeter. So think about it. What is one division of your vernier scale going to be? You divide 11 millimeters by 10, which is going to be 1.1 millimeter, So one vernier scale division will be 1.1 millimeter. Now 1 minus 1.1 is 0.1. Take the mod value always. So that is the least count. Is that clear? Everybody with me? Understood or clear? Awesome. So first step is always to find the least count. For finding the least count, you need to know one main scale division, one vernier scale division. Just subtract the two. Always take the modulus value. Don't worry which one is bigger, which one is smaller. Always the modulus value. So always try to find how much is the length of one division of vernier scale, because you will be given these many divisions coincide with these many divisions of main scale. So 11 millimeters is 10 divisions of, or 10 parts of vernier scale. So one part of the vernier scale will be divided by 10, which is 1.1. So 1 minus 1.1 is 0.1 millimeters. Is this clear? Very good. Awesome. Now the next thing is, understand, when you actually put something, you move this vernier scale either left or right. You move this vernier scale left and right till you fit this object over here, and then you take some readings. So say for example, this is your main scale. Something like this. Let's say this is 22. 23, 24, 25. This is 25, something like that. And your vernier scale below is something like this. And maybe it is something this way. Okay, maybe it is something like this. Okay, maybe this is 0, this is 1, this is 2, this is 3, this is 4, this is 5, so on and so forth. Then if this is your vernier and this is your main scale, then the main scale reading means on the main scale, what reading will you take? That reading where the 0 of the vernier coincides or crosses. Where is the 0 crossing? It is crossing after 22. 0 of the vernier, this 0 is beyond 22. So the main scale reading will be 22. How much will it be? 22. Is that point very clear, my dear warriors? Great. Then you have to measure what is the vernier scale reading. My dear students? The vernier scale reading is the vernier number, the markings which are there, which coincides with some division of the main scale. If you notice, this one is not coinciding with any main scale. This 2 is not coinciding. I think this 3 is coinciding over here. So the vernier scale reading is not 25, it is this number. The vernier scale reading is the reading on the vernier which coincides somewhere on the main scale. So the vernier scale reading will be 3. Vernier scale reading will be how much? 3. Is that very, very clear? Awesome. So now your final reading is always your main scale reading plus your vernier scale reading multiplied by the least count. Vernier scale reading is 3. Example, the least count is 0.1 millimeters. The main scale reading is 22 example millimeters. So our final reading will be 22.3 millimeters. 22.3 millimeters. Is that clear, my dear students? Awesome. Very good. So the reading is always the main scale reading plus vernier scale reading into the least count. So this is one formula which we saw. This was one formula which we saw, and the other formula which we have seen is your reading of vernier vernier caliper is always your main scale reading plus your vernier scale reading multiplied by your least count. So this is also a very important formula. Now the last thing over here is the zero error. Why does this zero error come? Maybe there is some fault in the instrument. When these clamps touch each other, ideally the zero should coincide with zero. Ideally both the zeros should coincide in that vernier caliper. But maybe it doesn't. That's the reason why you have something called as the zero error. So when the jaws are clamped, there are two possibilities. Maybe the zero of the vernier is to the right. The zero of the vernier is to the right of the zero of the main scale. This is one possibility. Other possibility is that the zero is slightly behind. So this, when the zero is ahead, then it is called as positive zero error. If the zero is behind, then it is called as negative zero error. Is this point very clear, my dear students? Is this point very clear? So if the zero of the vernier is ahead, it is positive. If it is behind, then it is negative. Now whenever there is a positive zero error, understand our vernier is already ahead. The vernier is already ahead by some distance. So whatever answer I get won't be correct. Whatever answer I get won't be actually correct. So what you should do is the actual length will be whatever reading you got from before. So from that you will have to take away something because already some value is there. Imagine you have to measure the mass of somebody. Already when nothing is there, it shows some 10 grams, or let's say it shows 1 kg. So if it already shows 1 kg when nothing is there, so when you put something on it, so you will take away 1 kg from it. Understood? So if my mass is 75, it will show 76. Why? Because it was already showing some value. So you will take away 1 kg from it so that you get the actual reading. So the L actual will be the reading minus the positive zero error. So when it is positive, you subtract. If it is negative, then the actual length will be the reading. It will be the reading, but when it is minus, what you will do? You will add it plus the negative zero error. Why negative zero error should be added? Imagine when nothing is kept on a weighing pan, it is showing minus 1 kg. So when I stand on it, if it shows 40 kg, that means my actual mass will not be 40. It will be 40 plus 1. Because when I was not standing on it, it was showing minus 1 kg. So it was showing negative value. So when I add 1 kg, then it will go to 0. When I add 40 kgs, then it will go to 39. Right? Understood? So that's why you have to add one number. I hope this is very clear. Understood? So this is how you tackle the errors. I have also put up your printed slide over here. Vernier scale least count is 1 main scale division minus 1 main scale division minus 1 vernier scale division, and vernier scale reading plus the main scale reading minus the zero error is the actual reading. These are the printed slides, but I feel you will be more comfortable with these slides which have handwritten. Okay, so I think it's a good time we solve some questions based out of this. A vernier caliper has 1 millimeter marks on the main scale. It has 20 equal divisions on the vernier scale. Which match with 16 main scale divisions. For this caliper, what is the least count? Okay, let's try to do this question. Everyone concentrate. 20 divisions on the vernier scale. 20 divisions on vernier scale is equivalent to 16 divisions of main scale. But the vernier caliper has 1 millimeter marks on the main scale. That means this will be 16 millimeters because each division is 1 millimeter. So 16 divisions will be 16 millimeters. Now this is for 20 divisions of your vernier scale. So therefore, 1 division of vernier scale, 20 divisions is 16. So 1 division will be 16 millimeters divided by 20. 16 with 4, 4, 20 with 4, 5, 4 by 5 of a millimeter. That is 1 division of vernier scale. But I want to find the least count. Least count is modulus of 1 main scale division minus 1 vernier scale division. 1 main scale division is clearly mentioned to be 1 millimeter. So this is 1. 1 vernier scale division, we just got it to be 4 by 5. 1 minus 4 by 5 will be just 1 by 5 of a millimeter. 1 by 5 means 0.2 millimeters. So hence the answer will be D option. Answer will be D option. Is that very clear, my dear warriors? Very good. Many of you have given the right answer, like I can see in the chat box. Keep it up. Keep it up. Moving on to the next question. In a vernier caliper, when the jaws touch each other, the 0 mark coincides. If this is given, what does it mean? The 0 marks in both the scales coincide means what? There is no 0 error. There is no 0 error, my dear warriors. Is that right? There is no 0 error, my dear warriors. Is that right? Correcto? Very nice. Very nice. Now, 10 vernier scale division matches the 9 main scale divisions. The length of the rod is measured using this so many divisions. Okay. So first thing, we should find the least count, I believe. Without least count, we should not proceed. Now, it is clearly mentioned 10 vernier scale divisions coincides with 9 main scale divisions. Correct? And each main scale division is 1 millimeter because it is clearly mentioned it is in millimeters. So this is also like 9 millimeters, but that is 10 vernier scale divisions. Therefore, 1 vernier scale division will be how much? You divide 9 millimeters into 10 parts. 9 millimeters into 10 parts. So my dear students, what's the least count going to be? 1 main scale division minus 1 vernier scale division. What is 1 main scale division? Well, 1 main scale division was 1 millimeter. 1 vernier scale division is 9 by 10 of a millimeter. So hence, what will you get? You will get 1 by 10, which is 0.1 millimeters. So that is the least count, but that's not the question. The question is, what is the value of that length? So the length, the value, the reading will be given by your main scale reading plus vernier scale reading multiplied by the least count. What is the main scale reading? Look at it. It shows 55 in main scale reading. 55 in main scale reading. So main scale reading is 55 millimeters because 1 division is 1 millimeter. What is vernier scale reading? It is clearly mentioned the 8th mark matches with the main scale. The 8th mark matches with the main scale. So that means vernier scale reading is 8 into the least count, which is 0.1, So won't it be 55? This was also in millimeters. So 55.8 millimeter. 55.8 millimeter, which is option A. Very good. Very good. So many of you answered it correctly. Awesomeness. Yes. Very nice. Now are you getting a hang of these questions? Shall we do one more question? I hope you have smashed the like button. If you are new to the channel, I hope you have subscribed to the Vedantu English channel as well. Very nice. Let's move on now to the next question coming up on your screen. Smallest division of the main scale of vernier caliper is 1 millimeter. And 10 divisions coincide with 9 main scale divisions. Okay, so first thing we'll do is finding the least count, my dear students. Standard procedure. Okay, so 10 vernier scale divisions coincide with 9 main scale divisions. 9 main scale divisions. And the division on the main scale is 1 millimeter. So 9 divisions will be basically 9 millimeters. So that is 10 vernier scale divisions. So 1 vernier scale division will be 9 divided by 10 of a millimeter. So the least count, which is 1 main scale division, minus 1 vernier scale division will be 1 millimeter. 1 millimeter is 1 main scale division. 1 vernier scale division is 9 by 10 millimeters. So I will get this as 1 by 10, which is again 0.1 of a millimeter. Which is again 0.1 of a millimeter. But there is a catch. When the jaws touch each other, just the 0 crosses on the main scale and second division coincides with the main scale. Oh, there is 0 error also. So 0 error. Is this positive or negative? Because it is given the vernier just crosses the 0. That means won't it be a positive error? Won't it be a positive error, my dear warriors? How many of you saw that? How many of you saw that? Very good. If you saw that, it is a positive error. Very nice. This will be again same main scale reading plus vernier scale reading into the least count. Main scale reading, it just crosses 0. So 0. Vernier scale reading, second division coincides with the main scale. Least count 0.1. So it will be 0.2 millimeters. That is your 0 error. What is the reading that I am getting when I put the object? Reading what I am getting with the object. You can see the vernier scale lies between 20 and 21. 20 and 21, that means it has crossed 20. Don't take main scale reading as 21. It has crossed 20. It's between 20 and 21. So main scale reading will be 20 millimeters. Vernier scale reading, 7th division of the vernier scale. So 7 into least count, which is 0.1. So that will give me 20.7 millimeters. But that's not the correct answer. The final answer will be what is the length or what is the diameter. The diameter will be 20.7. Because it's a positive error, you will subtract it. Positive errors are always subtracted. So minus 0.2. So it will be 20.5 millimeter. 20.5 millimeter, which is option number A. Everyone with me? Very nice. So now you have got how to do these questions based on vernier caliper, right? Always check for coinciding divisions. From that you find least count. Then 0 error if given, you find out whether it is positive or negative. Then the reading is given by mentioning which main scale reading is there and which division of vernier scale is coinciding with some division. So put those values and then either you add or subtract depending on whether it is positive or negative error. Now let's go to the next instrument. And the next instrument, my dear students, is none other than your micrometer screw gauge. Now in a case of a micrometer screw gauge, my dear students, this is also used to measure length, but the accuracy, the least count is much better. Okay, because this has usually a least count of the order 0.01, 0.001 kind of a millimeter. So you will see the least count is much smaller as compared to the vernier caliper, and that's the reason why you get very precise readings using a micrometer screw gauge. You have a U frame on a micrometer screw gauge. You have a circular sleeve or on which there is a main scale, and then there is a thimble which you can rotate. You can see there is a circular scale on it, that is called as the circular scale because there are some markings, some divisions on that circle. As you rotate, the circle rotates and it will also move forward. If you rotate the other way around, it will come backward. If you rotate one way, it will go forward. So you rotate and you will see it will keep on rotating and it will keep on moving in one direction. And on this main scale, you can find some divisions and some markings that will give you the main scale reading. On the circular scale, you can see the markings here. You will see the marking which will coincide on that flat line will be the circular scale reading. So how do I find out the least count of this? The first thing that you should know is something called as the pitch of the screw gauge. Pitch of the screw gauge. The pitch of the screw gauge is how much distance is moved by the circular scale upon the number of rotations. Meaning, if it so happens that I rotate the circular scale two times, and it moves by, let's say for example, 0.4 millimeter. Then the pitch of the screw gauge is 0.4 divided by 2, which is 0.2 millimeters. Meaning, how much does it move per rotation? When I rotate it once, it moves by 0.2 millimeters. That is the meaning of the word pitch. The meaning of the word pitch. That means when I rotate it once, how much does it move per rotation? Per rotation. Very nice. Now, the next thing is, once you get to know the pitch, get to know what is the pitch of it, then comes the least count. The least count of the screw gauge. The least count of the screw gauge. The least count of the screw gauge is nothing but whatever is the pitch divided by the total circular scale divisions. Total circular scale divisions. The total number of divisions on the circular scale. Meaning, let's say in this problem only, on that circular scale, there are some divisions, right? Maybe it starts with 0, 1, 2, 3 like that, and maybe it ends at 100, or basically last number will be 99, this number will be back to 100. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 like that, 98, 99 and back to 100. So you can see there are totally 100 divisions. 100 divisions on the circular scale. So think of it this way, one rotation it moves by 0.2 millimeters. One complete rotation it moves by 0.2 millimeters. So one division, if I move it, the circular scale, if I move it by one division, just one tick, not that entire circle, one small tick from one division to the next division. So that will be the least count. The least count will be 0.2 divided by 100. That is 0.002 millimeters. Is that understood, my dear warriors? Is that understood, my dear warriors? In this case, it will be 0.002 because the pitch was 0.2 millimeters. Pitch was 0.2 millimeters. Yes, very good, very good. Now, the final thing, and that is the reading. The final reading will be always just like before. The main scale reading plus your least count multiplied by, instead of vernier, here it will be circular scale reading. So you have to multiply this with circular scale instead of vernier scale. That's all. So it is possible that something like this, maybe it is given something like this. One second. This is, let's say, your circular scale. This is your main scale. Once again, put it in different colors, and something like this. And let's say over here it says so this is how it looks like. Example, this is your circular scale. And like you can see, this one over here is your main scale. Can you warriors tell me what will be the main scale reading in this? Can you warriors tell me what is the main scale reading in this? Come on, quickly put it up in the chat box. Put it up in the chat box, my dear warriors. Come on, put it up in the chat box. What do you think is the main scale reading? Put it up in the chat box. Yes, very nice. It has crossed 21. So yes, main scale reading is 21. And what about the circular scale reading? This is 40, 41, 42. You can see it is increasing over here. So it is basically 42. Example, I told you that the least count is 0.01 millimeters. Then what will be the reading, my dear warriors? The reading will be main scale reading, which is 21, so 21 millimeters, plus least count, which is 0.01 multiplied by 42 millimeters. So hence it will be 21.42 millimeters. 21.42 millimeters. That's all. Yes, that's the answer. Everybody understood how to get the reading of a micrometer screw gauge using the main scale reading and the circular scale reading? Right. So these were the formulas which you should know. Now one more thing comes over here, and that is the zero error. That is the zero error. Just like before, if the zeros coincide, if the zeros just happen to coincide on each other, then there is no error. When nothing is placed in between, the zeros coincide, then there is no zero error. But imagine this, it already shows some value on the circular scale. You can see already there is some value which is shown. Maybe here it is 3. So because it is already showing some value, that's why it is a positive zero error. That's why it is a positive zero error. And if it is behind, you can see it has gone on the negative side. It has gone on the negative side. This 0, you can see it is showing some minus value. Basically, it is the previous rotation's value. This is the previous rotation's value. Then this is considered as negative zero error. And just like before, you can add and subtract to get the final length. So the final length will be reading, and if it is a positive error, you will subtract it. Positive zero error. This will be your positive zero error. And if it is negative, then you will add it. If it is negative, then you will add it. So this is your negative error. Negative error is always added, positive error is always subtracted to find the length, my dear warriors. Cool? So keep this in mind. Let's solve some questions based on this so that you will get an idea. A student measures the diameter of a small steel ball using screw gauge of least count this much. The main scale reading is 5 millimeters and 0 of circular scale division coincides with 25 divisions above the reference level. If the screw gauge has a zero error of minus 0.004 centimeters, then the correct diameter is. So we have to find everything over here. It is clearly mentioned what is the least count. The main scale reading is given, 0 coincides with, that means there is some zero error. All right. So let's start by finding what is the zero error. The zero error is basically minus 0.004 of a centimeter. Minus 0.004 of a centimeter. I think over here what we need to do, every calculation is in centimeters, not in millimeters, so be careful about it. So just be little bit careful about it. Next thing what you need to take care of is the actual reading. The main scale reading is this much and circular scale division coincides with 25 divisions above the reference level. So the reading will be main scale reading plus least count into circular scale reading. What is the main scale reading? The main scale reading is nothing but 5 millimeters. It is nothing but 5 millimeters. Is that clear? Everybody with me? The main scale reading is nothing but 5 millimeters. Very good. Next thing, what is the least count? Least count is already given to be 0.001 centimeters. What is the circular scale reading? Circular scale reading is 25. It is given the 25th division of the circular scale is coinciding. So this is into 25. So how much will this be? This will be 0.025 centimeters. Every answer is given in centimeters. So this millimeters also I'll write it as 0.5 centimeters. So this will be nothing but 0.525 centimeters. 0.525 centimeters, which is, I think, there is one zero error also. I have to add that or subtract it. We'll take care of it as well. So first of all, the reading that I got was 0.525 centimeters. Because the zero error is nothing but negative. So when I find the final answer, what I will have to do? I'll have to add it. So whenever the error is negative, I will add it. So my dear students, I'll have to add 0.004 centimeters. That will make it 0.529 centimeters, which is option D. Is that clear? Everyone? Very nice. Many of you have written down D as the correct answer. Very good. So zero error was negative, that's why we added. If this was plus, I would have subtracted. Okay. Catch was some things were in millimeters, something were in centimeters. The moment I saw least count is in centimeters, I realized that okay, since options are also in centimeters, we have to keep everything in centimeters, not in any other units. Let's go to the next one. Okay, everybody, get ready for this. All right. Screw gauge with a pitch of this much, circular scale with these many divisions is used to measure the thickness of a sheet. Before starting, it is found that the two jaws, when they are in contact, 45th division is in line and the zero is hardly seen. Okay, zero error is there. What is the thickness if main scale reading is this much and 25th division coincides? Alright, let's start by finding the least count of this. Least count is always the pitch upon the circular scale divisions. What is the pitch? The pitch is 0.5 millimeters. How many circular scale divisions are there? 50 divisions. This 5 cancels. So this will become 0.01 millimeter. That is the least count. How many of you wrote the least count is 0.01 millimeters? Yeah, the question size does not matter. Don't worry about the question size. What matters is how are the steps. The steps are very straightforward. The questions look very, very big. Don't get scared by that. Next thing, what is the zero error? Because it is clearly mentioned that the zero is barely visible, that means the zero error is negative. You can hardly see it. So, my dear students, the 45th division coincides on the main scale line. What does that mean? The main scale reading is 0. Least count is 0.01 into what should I do over here? Come on, think about it. What should I do over here? Should I multiply it by 45? Because 45th division of the main scale coincides? No, that is the catch. Look over here carefully. When you have negative zero error, you can see this is 0, and if you go behind, those are negative values. Or from the previous rotation. So when this 45 comes over here, basically from 0, you are behind by 5 units. Ideally, the 0 should have coincided, but because the 0 has gone ahead, so you are getting a negative value over here. That means you are behind by 5 units if there were 50 divisions. So technically, it is not 45th division. This 45th division will become the 5th division. Understand that. Let me mention this very, very clearly over here. So if you have your circular scale, if you have your circular scale and this is your 45, then 46, 47, 48, 49, 50. 50 will become again back to 0. Again that 1, 2, 3, 4, 5, 6 like that. Again it will come to 45 like this. And this is how the main scale reading is. This is how your main scale is. So this 45 technically is 5 readings behind. Is basically 5 readings behind. This is why you are getting that negative error. Is this concept understood? My dear warriors? Yep. For positive error, it was not a problem. For negative error, it becomes a headache because you are going in the previous rotation. You have gone by 5 units behind. Okay, so how much is the zero error? It is basically 0.05. What was this? This was millimeters. So this is also in millimeters. So that is your zero error. What is your actual reading that you get? What is the actual reading that you get? Obviously main scale reading plus least count into circular scale reading. Main scale reading. The main scale reading is 0.5 millimeters. So 0.5 is here. Least count is 0.01. 0.01 multiplied by circular scale reading. Circular scale is 25. So into 25. So this will become 0.5 plus 0.25, which is nothing but 0.75 millimeters. 0.75 millimeters. But don't mark this. But don't mark 0.75 because there was a zero error. So the final length or final answer, won't be 0.75 minus because it is negative, it will be plus. So negative errors are added, positive errors are subtracted. So plus 0.05, which will make it 0.80 millimeters. So that is the final answer. 0.80 is option number A. Is that understood, my dear students? Is that understood, my dear students? Yes, option number A. Very good. Yes. So these kind of questions are very common in your competitive exams. You will see many type of questions are there. The size is very big, but if you follow the steps, finding the least count, then finding zero error, then finding the reading, then adding or subtracting the zero error, you will reach the final answer. Okay, I think now these things are much easier for all of you, and if you feel that I have made it easier by solving these questions, give me a thumbs up and smash the like button. I'm seeing the like counts here. Make sure you're smashing the like button as well. Right. Let's move on to the next one. And that is basically your simple pendulum. Now, in case of a simple pendulum experiment, the aim is to find, the dissipation of energy by plotting a graph between the scale of amplitude versus time. Okay, let's understand this. You take anything which is hanging, and leave it. It will go back and forth. Like a pendulum. But because in reality there are negative forces, dissipative forces. Dissipative means which suck away the energy. You will see slowly the oscillation will become smaller and smaller and it stops. So earlier the amplitude will be huge, so the energy will also be huge, and then slowly you will see that the amplitude becomes smaller and smaller and then it stops. So if you happen to plot the graph of how the amplitude changes with time, you will see it looks something like this. This is time, this is your amplitude. You will see that the amplitude varies like this. This is your amplitude. You can see the amplitude earlier was good, then it became smaller and smaller. In fact, you can also plot the graph of energy with respect to time. The graph of energy of the oscillation with respect to time. Then that graph also looks very similar. The energy of the graph with respect to time, actually it will look very similar. It will look something like this. First it will have maximum energy, then the energy slowly goes off. It will have maximum energy, then slowly the energy will go off and it will tend towards zero. So here I can say the energy tends to zero as time becomes very large. That means time tends to infinity. This is how the energy graph looks like. So you can see the energy is not constant. Why is the energy not constant? The reason is the energy is not constant since mechanical energy is lost due to frictional or viscous forces. These forces are present everywhere around us. No matter what you do, you cannot get rid of these forces. You cannot get rid of these viscous or drag forces. And these viscous forces, these viscous or dissipative force is given by Fd, which is minus B times of V. V is velocity. What is B? B is basically called as your damping constant. B is basically called as your damping constant. Some constant. If B is very large, that means the force for retarding it is very, very large. If B is small, that means the resistive, the dissipative forces are very, very less. Why is it called dissipative? Because energy is lost. Energy is not constant. Energy is slowly lost to the surrounding. So you are dissipating it. That's why dissipative force, drag force, damping force, whatever. Okay, you can also call it as damping. You can also call it as damping force is minus B times of V. V is the velocity. More the speed, more is the damping force. More the speed, more is the damping force. Now, it so happens that the amplitude which decreases over time, it follows this equation. The amplitude is A naught into e to the power minus bt by 2m. E to the power minus bt by 2m. This is the exponential decay form. Why am I saying exponential decay? Because you might have seen maybe in first order kinematics of chemistry, or even in radioactivity law, n is some constant e to the power minus something into t, and there also the number of elements in the radioactivity, it reduces, or even in first order kinematics, the concentration reduces with time like this. So this is also a very, very similar equation. The amplitude keeps on reducing and becomes close to zero as time progresses. What is B? B is the damping constant. B is nothing but your damping constant. What is M? M is nothing but the mass. M is nothing but the mass. Is that clear? Okay. Now, if this is true, then we also know that initial energy of any SHM is half k A naught square, is half k amplitude square. Isn't that right? So if I ask you what is the energy at any given time, you will be like, sir, it is half k A square. Okay, but wait a minute, what is A? A is this whole thing. A is this whole thing, which is A naught into e to the power minus bt by 2m, right, whole square. So what will I get? I'll get half k A naught square into, because I'm squaring it, it will become e raised to minus bt by m. 2 cancels. Half k A naught square is E naught. So therefore, I will get E is equal to E naught into e to the power minus bt by m. This is also decaying. This is also reducing exponentially. This is just like first order kinematics equation, where that quantity reduces till it becomes zero, my dear students. Yep. So you will see that this graph of energy with respect to time is like this, perfectly matches, and you can see the amplitude was large here and slowly it kept on reducing and finally it tends to zero. So my dear students, understand over here, this is the amplitude, this was the amplitude, then 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 this was the amplitude. Amplitude is the extent till which it goes back and forth. So slowly the amplitude is reducing. So this particular curvy nature was showing how the pendulum is going left and right. Then slowly the left and right amount is reducing till it becomes a big fat zero. Is that clear? Yes. Now, a lot of students have this confusion, sir, damped oscillations is deleted. You know, that's what is funny in the syllabus. Damped oscillations and LC oscillations are also not there in the syllabus, but this experiment is there. So if at all a question comes, I feel we should be on the safer side, then you need to know this equation, you need to know the energy equation, you need to know energy is half Ka square in SHM, that though you will anyway study. You should know how the graph looks like. That's all that is important. What kind of questions can come? I have put the same thing in the printed slide. Look at this. Look at this. To be on the safer side, we are doing these questions because it is very funny, because on one side in SHM, damped oscillations is deleted, but here they have put it in experiments. A simple oscillator undergoes damped oscillations and a graph is plotted between square of amplitude versus time. If the amplitude reduces to half in 10 seconds, then the energy would have dropped by how many times at 10 seconds, and what time will the amplitude be? 1/4 of the initial value. Okay, observe this carefully. It is clearly mentioned that the amplitude reduces to half in 10 seconds. We know amplitude function is A0 e to the power minus some constant into time. Doesn't matter, bt by 2m, b is a constant, 2 is a constant, m mass is a constant. So I'll assume it as a number constant, which is c. Because the amplitude becomes half in 10 seconds, that means A0 by 2 is equal to minus e to the power minus ct, is equal to A0 into e to the power minus ct. A0 cancels, this will become 1 by 2 is e to the power minus ct, So minus power means I can bring it down also. Minus power, that means I can also bring it down also, right? We can do all those calculations, but I don't think we'll be needing it for now. One of the questions says, when will the amplitude be 1/4 of the initial? When will the amplitude be 1/4 of the initial? So if I use this equation, if it becomes 1/4 of the initial, then A0 by 4 will be same term, A0 e to the power minus ct, A0 e to the power minus ct. But wait a minute, e to the power minus ct. Okay, I don't know the time. One more thing. It became half in 10 seconds. That means this time over here, I can just put it as 10 seconds over here. So this will become nothing but 10c. E to the power minus 10c is basically half. Interesting. So why can't I write it as e to the power minus c whole raised to 10? E to the power minus c whole raised to 10. Is that right, everyone? Because at 10 seconds the amplitude became half. So from this I got an idea. That e raised to minus c whole raised to 10 is half. That means e raised to minus c will be 1 by 2. 1 by 2 whole raised to 1 by 10. 1 by 2 whole raised to 1 by 10. I'm taking 1 by 10th root. 1 by 10th root on both sides. So over here, can I not do this? This will be A0 into e to the power minus c raised to t. This A0 got cancelled. So 1 by 4 is equal to e raised to minus c is nothing but 1 by 2 whole raised to 1 by 10. And this whole thing raised to t. Everybody with me? Well, if you go by this method, you will get to the answer, but after a long time. Instead, I will tell you a simple trick. I'll tell you a very simple trick. You want to do this, you can do it, but it will take you a long time. Instead, the trick is to remember the principle of radioactivity. I know it is not there in the syllabus, but still you will learn it for the sake of this problem. If you have a concentration n or quantity n and it is decaying exponentially like this, then understand after exactly half-life, the quantity becomes original by 2. Whatever was the original, it will become half of that. It will become half of that, that means n0 by 4, after 2 half-lives. After 2 half-lives. Oh, now the problem looks very simple to me. The quantity became half after 1 half-life. It became 1/4 after 2 half-lives. This half-life only was given to me as 10 seconds. So obviously 2 half-lives will be 20 seconds. Hence, the answer will be, for this particular question, at what time will the amplitude be 1/4? Will be 1/4. The answer will be nothing but 20 seconds. That will be a much easier. Is that clear? Is that clear? Yes. It is much better. It is much better. So, you know the way they have deleted the portions also. If you know those deleted concepts, it will be helpful for you to solve the questions. If they ask you when does it become 1/8, 1/8 means half of that, so it will take more 10 seconds, so 30 seconds. So after 30 seconds, it will become n0 by 8. It will become n0 by 8. So that is a much easier way to solve the question. Then, if the amplitude reduces to half in 10 seconds, the energy would have dropped by how many times in 10 seconds? We know that energy is half K(A) square. So if the amplitude becomes half times, the square of half will become 1/4. So if RHS becomes 1/4, energy will also become 1/4 times. So the energy would have dropped by how many times in that time? 10 seconds, 1/4 of the times. And how will the graph of A square versus time look like? It will look like this. It will look like this. Is that clear, my dear warriors? Exactly this curve. Exactly this curve. Amplitude, energy. Remember, even energy is proportional to A square. Energy is proportional to A square. So you will see that the graph will anyways look like this only. Very good. Yes. All right. This is the first time on the English channel. Please understand that. Yeah, no English channel has done this, right? Okay, come on, let's move on to the next one. Okay, coming up on your screen, and that is meter scale principle of moments. Meter scale principle of moments. Okay, so in this, the simple funda of torque is used, nothing more, nothing less. You have a meter scale, you have a known mass, you have an unknown mass, you balance the meter scale, and then whenever it is balanced, you mark the readings, and once you mark the readings, you will be able to use the equation of torque to find out the unknown mass, or to find out, you know, the length at which it balances itself. Like for example, over here, this is the fulcrum, this is the pivot over here. There is a known mass which is at some distance from the fulcrum or the pivot, and there is unknown mass or known mass at another point, and it is at some distance from the pivot. So when it is balanced, when it is basically balanced, understand that the net torque will be 0. That means all the torques anti-clockwise will balance all the torques clockwise. All the torques clockwise. So if the anti-clockwise torque, if you see this mass is trying to rotate it anti-clockwise, this mass weight is trying to rotate it anti-clockwise, understand that the torque will be R. R over here is the distance from the pivot point, which is X, into basically mg, will be equal to, here R is this much, the force over here, the mass over here tries to rotate it clockwise, so the torque produced will be nothing but Y into that unknown weight. So solving this, you can find the value of W, which is nothing but X mg divided by Y. Is that understood, my dear warriors? That's all. Okay, I hope this is clear. I hope this is very clear. Cool. So the torques need to be balanced. So R cross F anti-clockwise will be R cross F clockwise. That's all. That's all. So let's have a look at some questions. Let's have a look at certain questions. What is this particular question? Observe carefully. It says there is a meter scale which weighs which has two weights, 12 grams and m grams. I think 12 grams is here. This is not 10. This is not 10. This is 12, I believe. 12 grams and unknown mass m at 10 centimeters. Yes, at 10 centimeters and 80 centimeter at 80 centimeters. So that another unknown mass will be m grams, will be n grams. Okay, 50 grams is the weight of the meter scale. Find the unknown mass so that the meter scale stays balanced. Now, if I hinge it or pivot it here, the weight of the meter scale does not matter because the weight itself passes through the pivot point. So there is no torque due to 50 gram weight of the scale. The scale also has some weight, remember that. But if the fulcrum was somewhere else at 40 or 60, then that 50 grams will give a torque that you will have to count it. Here that won't matter. Alright, so what are the different distances from the pivot point? This is 10, this is 50. So how much will this distance be? This will be 40 centimeters. This will be 40 centimeters. From 50 to 80, how much will this be? This will be 30 centimeters. So the torque this way should balance the torque the other way. Torque this way will be R cross F, which is 40 cross 12 grams, is equal to, if you are wondering, sir, what about the units? Don't worry. If I put centimeters on left hand side, I will put centimeters only on the right hand side. So 40 centimeters into how much grams? 12 grams. 12 grams is equal to, torque from the other side will be R cross F again. R is 30 centimeters into m grams. Now 0, 0 cancels. M will be 4 into 12 by 3. 0, 0 has cancelled. This goes this. This will become 4. So it will become 16 grams. So the mass will be nothing but how much? 16 grams. Is that right? Everybody with me? Understood or clear? Oh? Very good. Everybody has put it up. Yes. Awesome. 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 Okay. Unable to write the question. Don't worry, even if you are unable to write the question, we'll be giving the PDF later on so that later on you can see the question. You don't have to copy down all the questions, okay? We'll be giving you all the questions. Yeah, very simple kind of questions come on this. There is nothing great in this. Answer given here was wrong, don't worry. Next experiment is finding the Young's modulus using Seal's method. So in this, what happens is you hang a wire and you have some basic mass on it or some standard mass on it, and besides it you hang the same wire but with an extra mass on it, and see how much does it extend. Based on how much it extends, you can find the modulus of elasticity, meaning the Young's modulus. So Seal's method is used to measure the Young's modulus of the wire which is hanging. Why do you need two wires? Reason is, sometimes it might happen that due to temperature variations, the rod or that wire might extend naturally because of thermal expansion. So to offset that amount, so as to neglect the expansion due to thermal but only due to the load, that's why you have another wire which is exactly identical, and with respect to that you measure how much is the extension. Because if the temperature on that day is more, both the wires will extend. If you add load on one side from that test weight, on the test weight side, then there will be more extension. So noting down the difference, you can get what is the total extension only because of the load. Is that clear? Why this happens? So you can see there is a control wire. Control wire means standard wire. There is a test wire where you actually put the weight. So when you add the weight, you can see it goes down a little, and noting down the difference between these two wires, you get the extension in the wire only due to the weight, not the thermal expansion. So there can be a question, why is the control weight or the control wire used? It is to offset the effect of. So the control wire is used to offset, is used to offset the effect of thermal expansion. That is the line that you will put, thermal expansion, as simple as that. Great. So what is the final formula that you get for Young's modulus? Because we know Young's modulus is stress by strain, and stress is the force by area, strain is nothing but extension by original length. So force is nothing but mg, area is nothing but pi r square, r is the radius of the wire, x is the extension, L is over here. So that is your Young's modulus. That is your Young's modulus, mgl by pi r square x, same thing, mgl by pi r square small l, one and the same thing. Sometimes there can be questions on errors on this, questions on error or percentage error in these type of formulas, where you might be asked to find what is the relative error or percentage error in the Young's modulus. In that case, what you will do, write it in the power form. Write it in the power form. So this will become m raised to 1, g raised to 1, l raised to 1, r raised to minus 2, x raised to minus 1. The whole thing divided by pi, which is a constant. Each of them might have errors. Each of them might have errors. So you will get many terms of relative error here. So first is mass. The power is 1. So 1 into delta m by m will come. If gravity has error, then 1 into delta g by g will come. If the length of the wire has an error, so 1 into delta capital L by L will come. If radius has an error, don't take the negative value, always the positive value. So 2 times the delta r by r will come. Excess power minus 1, always take the mod value. So 1 into delta x by x will come. That's how you find the relative error. That's how you find the relative error. That's all. Okay. Okay. How we get 40 centimeter in the meter scale example? That was very straightforward. Where did it go? This is at 10 centimeter mark. This is at 50. So 10 and 50, what is the difference? 40, right? So from the pivot point, how far are you? 30. This was 80 centimeter mark from 50. So what is the distance between 50 and 80? 30. I hope that is very, very clear. Is this point clear, my dear students? In fact, you should remember general formula for errors. If a physical quantity is some constant into P1 raised to alpha, P2 raised to beta, P3 raised to gamma, then delta P by P, relative error in P, constant does not matter. First power will come into delta P1 by P1. The next power will come into delta P2 by P2. Doesn't matter whether you're below or on the top, always take the positive values, delta P3 by P3. So this is the error formula which you will generally use for all kinds of questions. Okay, so the same thing has been mentioned here. It is used to find the Young's modulus of that wire. Let's have a look at some question coming up on your screen. In a method of Seal's experiment, the diameter is measured with least count this much and is found out to be this much. Length this much. Okay, least count is that much. Weight is suspended. Okay, extension is given. So least count is this much. Find the error in the measurement of Young's modulus. So exactly whatever we had seen over here, same thing has come as a question. You can see right over here. So start off with the formula of Young's modulus. It is mg length divided by pi r square into extension. So the error in y percentage wise will be, mass does not have an error. Notice 50 Newton is a fixed value. There is no error in the mass. So ignore that mass. Even G does not have error because it is not given. The total weight is only mg, which is 50 Newton. So no error in mass, no error in G. Did you understand it? So these two quantities, you can see there is no error. There is no error whatsoever. So don't even think of writing them. Length has some error. So delta L by L. Pi is a constant. Don't bother. R's power is 2. So 2 times delta R by R plus delta X by X. This whole thing, because we want to find it in percentage, so into 100. The length is measured with a least count of 0.1. So the error in the reading will be 0.1. the length value is 110. So I'm just going to put 110 over here. 2 times delta r by r. Look at it. Look at it. The diameter is measured to be this much with a least count of this much. Let me tell you over here, since the diameter is 2 times of radius, therefore delta d by d is also delta r by r. That 2 is a constant, it will not come. Okay, so delta d by d is delta r by r. So the relative error in diameter will be same as the relative error in radius. So even if diameter is mentioned, don't worry, you can also use it for radius. So what is that delta r by delta r by r? Least count is 0.001, whole thing divided by 0.05. That's what it is. Plus the extension is measured to be this much, least count is this much. So what is the least count? 0.001 and extension is 0.125. The whole thing into 100. That will be in percentage. You solve this, you must get it as 4.89%. 4.89%. That's what it is. Is that very clear, my dear students? Okay. I hope this is clear. I hope this is very, very clear. Why mg has zero error? Because did they say 50 Newton plus minus some percentage? Did they say the weight is this much with a least count of this much? No, because they did not mention anything about the weight, whether there was error, whether there was some percentage error, whether there was some least count in the measurement. Hence, you will assume it as no error. Hence, you will assume it as no error. Yes. Units are same. Yes, that's the reason why we are dividing centimeter, 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 centimeter. So when I divide it, no problem. There is no problem at all. Okay. Is that very, very clear? Is that very, very clear? So if you know all these chapters, it becomes a little bit helpful for, understanding these concepts. Else, if you have no idea what Young's modulus is, then it will be little bit tough. Okay. Now, surface tension of water capillary rise method. This is also another experiment which is generally asked or given, where you put a capillary tube inside a liquid. You will see that the liquid rises up by some height, and that happens because of the phenomena of surface tension. Surface tension is nothing but a property of the liquid where the surface tries to minimize itself. It tries to reduce its area as low as possible. If it so happens that you dip a pipe in a liquid, and you find that the meniscus, that means the surface of the liquid, is concave up, then you will see that the liquid inside that pipe rises up by some height. This type of liquid has an acute angle of contact. This is called acute angle of contact. Acute angle of contact. You can see with the surface, this curved nature, that theta which is there is less than 90 degrees. The best example for this is water. When you pour it in a glass tube, it makes an acute angle of contact and the water goes up. This is the height by which the water goes up. Whereas liquids like mercury, you will see that their curvature is convex up. The surface of the liquid, which is also called as meniscus, is convex up. This is concave up, this is convex up. Such liquids, you will see, will go down. There is a dip in it. So here, if you notice, the angle of contact is more than 90 degree. So the angle is obtuse. So it will be dipping. The best example is mercury in glass tube. Similarly, you also see that there are some liquids which are perfectly flat. Theta is 90 degree. It neither goes up, neither goes down. So the height rise or dip is zero. Example for this is water in a silver container. It neither goes up, neither goes down. It is exactly at the same level. That's the difference between the two. Okay, so there are three kinds of liquid: acute angle, obtuse angle, and 90-degree angle. Depending on the angle of contact, the water or the liquid will go up or go down, or will not go up or down at all. That angle of contact is the angle which is made by the liquid and the solid surface. Angle made by the liquid and the solid surface inside the liquid. You can see that right over here. It is made inside the liquid. Whatever is the angle between the liquid and the solid surface inside the liquid, that is the meaning of angle of contact. You don't have to worry about what is angle of contact. In case you do not know only what is surface tension, then you have to go back to the entire chapter, read from beginning what is surface tension, what is cohesion, what is adhesion, what is all these things. So if you have not read that chapter, then this might sound a little bit out of the box. Okay, so it so happens that the height rise or the dip in the liquid inside that small tube is called as a capillary. Capillary means a small tube which has an opening on both sides, so the liquid can easily pass through it. That is a capillary. Is given by 2s cos theta by rho gr. 2s cos theta by rho gr, where that S is nothing but your surface tension of the liquid. S is nothing but the surface tension of the liquid. Theta is nothing but angle of contact. Angle of contact. What is R? It is nothing but the radius of the capillary tube. The radius of the capillary tube. This radius which is there, that is the radius of the capillary tube. Is that okay? The radius of the capillary tube. G is gravity, rho is density, h is the height by which it goes up or falls down. Now it so happens that for the same liquid, if you use different sizes of radius or the capillaries, you will see the height rise or fall will be also different. Reason being, since h is 2s cos theta by rho gr, h is inversely proportional to r. H is inversely proportional to r. That's the reason why if you draw a graph of h versus r, it will look something like this. You can be asked a question on that. Yes, you can be definitely asked a question on that. In fact, I think there is a question on this. No. Okay. You can be asked a question on draw the graph of height rise in the capillary versus the tube sizes, capillary sizes. More the radius, less the height. Less the radius, more the height. So this thin tube, height rises more. Wide tube, the height rise is going to be less. Is that right, everyone? Cool? Very nice. All right. Let's move to the questions then. A capillary tube of a uniform bore is dipped in a water which rises by 7 centimeters. Find the radius if the surface tension is this much. Now, usually the angle of contact for water and glass is not just less than 90, but it is very close to 0 degree. This is a value which you must remember. The angle of contact is like 1 degree, 5 degree, 2 degree, like that. Very small. So because it is so small, I will almost assume it as 0 degree. Meaning the water surface will almost be like this over here, and you can see the angle made at this point is almost like 0 degree. So now the question is, find the, what do you have to find? Find the radius of the capillary. So height is 2s cos theta by rho gr. So r will be 2s cos theta by rho g into h. Now 2, as it is surface tension, I don't know. Cos theta will be cos of 0. Cos 0 will become 1 later on. Density of water is 10 to the power 3. G value is 10. Height is 7 centimeter. So 7 into 10 to the power minus 2. What about surface tension? Observe carefully. 70 dynes per centimeter is 70. 1 dyne is 10 to the power minus 5 Newton. And per centimeter, 1 centimeter is 10 to the power minus 2 of a meter. So minus 2 minus 5 becomes minus 3. With 1 0 will become minus 2. So 7 into 10 to the power minus 2 Newton per meter. So I will put over here 7 into 10 to the power minus 2. 7 into 10 to the power minus 2. This will give me the radius. 7 7 will cancel all those things. How much will the answer come out to be, my dear warriors? How much will the answer come out to be, my dear warriors? Just check it out. This 1 0, this will cancel. I think it should be coming out as just 0.2 millimeters or something. It must be just coming out. Yes, it is coming out as 0.2 millimeters. It is just coming out to be 0.2 millimeters. Is that okay, my dear warriors? Is that okay, my dear warriors? Understood? Oh, clear? Oh, can we move ahead? Yes. Awesome. Awesome. Very nice. Very nice. So these are the kind of questions you can expect in your surface tension height rise in capillary tube. Now the next kind of question. Yes. Capillary is basically a small tube with an open bore, so the liquids can pass through it. Capillary. It's a small tube. Both sides are open. Okay. Water can go in and come out from the other side. That's all what a capillary is. Alright. Coefficient of viscosity. Determination of coefficient of viscosity by dropping a ball in a tall container. When the raindrops fall from the clouds, they come down at a constant speed. They come down at a constant speed. That constant speed is called as the terminal speed. That constant speed is called as the terminal speed. So what happens is, initially when you drop a ball, it accelerates and it starts from rest. But as soon as the speed increases, once it acquires speed, you will see that there will be a viscous force which comes into play. That viscous force will give it a reduced acceleration. Reduced acceleration. So the acceleration will not be as before, it will be having some lesser value. As it goes more down and down, you will see that the viscous force will become large. The viscous force will become large, and then you will see that the acceleration will become 0, and that's the reason why, because it is not accelerating, the velocity will just become a constant value, which is called as terminal velocity or speed. Terminal velocity or speed. Earlier it starts accelerating because of gravity. Gravity pulls it down. It starts going down. As soon as it starts going down, viscous force starts acting and the speed increases. Viscous force also increases till they all balance each other, and you see there is no net force. So there is no net acceleration, and that's why it comes down at constant speed. It comes down at constant speed eventually. That is called as terminal velocity. The formula for terminal velocity is 2 by 9 pi r square, 2 by 9 r square g sigma minus rho by your eta. 2 by 9 r square, alright, very important, 2 by 9 r square, right, g sigma minus rho by eta, where this sigma is your density of that ball which is being dropped. This is density of the liquid. Density of the liquid. G is G, R is the radius. This is nothing but the radius of that ball. What is this eta? This is your coefficient of viscosity. Coefficient of viscosity. Coefficient of viscosity. This will give you the terminal speed. As simple as that. Very simple. No, terminal speed is not 6 pi eta RV. That is wrong, Roshan. Yeah, be careful. Yeah. So when terminal speed is achieved, remember one thing. When terminal speed is achieved and the ball is going at a constant speed, that means the acceleration is 0. Then the weight is being balanced by the buoyant force and the viscous force. Weight is mg, buoyant force is volume into density of the liquid into g, viscous force is 6 pi eta RV. V is that velocity which is terminal velocity. Very, very important. Viscous force is 6 pi eta RV. This is actually your Stokes law. Buoyant force is V rho G, volume into density into G, and the weight will be just mg. Weight will be just mg. Yes, keep these things in mind. Keep these things in mind. Okay, very, very important. Let's see. Plot the graph of speed versus time for a ball falling in a viscous fluid. This has come so many times in many competitive examinations. Plot the graph of velocity versus time. How will it look like? First, it will be 0. Speed increases, but then it slowly stops increasing. It will reach something called as the terminal velocity. So the graph is a curved line because initially it increases, but then it won't increase so much because acceleration is reducing. So you can see that by drawing the tangent. Here the tangent will be like this, here it will be like this, here it will be like this, here it will be like this. Finally it will be 0. Remember the tangent's slope over here is nothing but acceleration since it is dv by dt. So the slope is reducing. Finally you can see a is 0. Here first there is large acceleration, small, and then becomes 0. That's the reason why the graph is a curved line. Got it? Very, very important. Next one. If a ball is dropped, has a terminal speed v, and then the ball of double its size has a terminal velocity of how much? Ball double the size has a terminal velocity of how much? Straightforward question, my dear students. Velocity is nothing but 2 by 9 r square g sigma minus rho by eta. So velocity is proportional to r square. So think about it. If radius is doubled, the square of it is made 4 times. So if RHS becomes 4 times, even the LHS should become 4 times. Hence the answer must be 4V. Very nice. Great. I hope this is very, very clear. Thank you for reminding me to have water. Okay. Let's move to the next one coming up on your screen. Speed of sound, resonance tube. Finding the speed of sound using resonance tube setup. Now, in this particular setup, what happens is you use a tuning fork, you use an open pipe, you dip it inside water usually, and you take out the tube slowly and place your ear and try to hear a loud sound by smashing the tuning fork somewhere, and you know the tuning fork is hit somewhere, so the tuning fork vibrates. So when the vibration occurs, you will see the sound will go inside, and once it goes inside, because it encounters a water surface over here, that sound which travels inside will get reflected back here. So now you have two sounds, one sound which is going down, one sound which is reflected up. Because you have two waves going in the opposite direction, they will interfere and create a standing wave. And the standing wave will be in resonance only under certain conditions, only if it matches certain lengths or if it is having certain frequency, only then it will, encounter resonance, where these two waves, which is incident from the tuning fork and the one which is reflected back from the water surface, only then they will encounter interference which is producing resonance in that standing wave. So for that to happen, what are the conditions? Well, first thing, because this part will behave like a closed end, hence there must be a node over there. Second thing, this is an open end, that means there must be an anti-node over there, because the sound which is incident from the tuning fork, this is incident, is getting reflected from the closed end like this. This is reflected together will produce a standing wave, and for resonance for resonance, the condition is the frequency should be odd times velocity of the sound divided by 4 times your effective length. This is the formula for resonance, my dear students. Frequency of the tuning fork is odd times velocity of the sound by 4 times the effective length. This F is the frequency of your tuning fork. Tuning fork, very, very important. This is the formula. First thing you should know about this. This odd number decides harmonics. If odd number is 1, if the odd number is 1, this is the first harmonic. First harmonic. Then the next odd number is 3, so that will be the third harmonic. Third harmonic. Then the next odd number is 5, so fifth harmonic. So only odd harmonics are present in case of a pipe which is closed and open on both sides. Closed and open on both sides. Keep that in mind. Now understand how this works. How this works. I am going to draw it for you rather than showing you ready-made diagrams. When the pipe is completely immersed in the liquid, when the pipe is completely immersed in the liquid, let me show the liquid level like this. You hit the tuning fork, you will not hear anything, there will be no resonance. So you slowly take out that pipe, slowly take out the pipe out of the water. You might not hear resonance. As you take it out more, maybe the first resonance might occur when you see a standing wave being formed this particular way. This particular way. Here you have an antinode, here you have a node. This is exactly at lambda by 4. This is your first harmonic. This is your first harmonic where you have an antinode and a node over here. You take it out further. You take it out further, maybe over here, something like this. Then you might get the next harmonic slowly. Something like this. Yes, this is antinode, again a node, again antinode, and again a node. So this wavelength is lambda by 4, lambda by 4, lambda by 4. So 3 lambda by 4. This is your third harmonic. Third harmonic. See if this is very, very clear. Why is this lambda by 4? Because when you draw one wavelength, then you will see you will have 2 lobes. You will have 2 lobes. This is one wavelength. So if you just consider only this much part of this, this is obviously lambda by 4 divided into 4 parts. That's why this is lambda by 4, not lambda by 2. So like that, 2 halves and 1 half. So 3 such parts are there. So 3 lambda by 4. Is that clear? Why is it lambda by 4 and 3 lambda by 4? Is it clear why is it lambda by 4 and 3 lambda by 4? Okay. Next one you will get 5 lambda by 4, fifth harmonic, 7 lambda by 4, seventh harmonic, so on and so forth. Now the length which is above the water surface, if I call it as L1 here, length which is above the water surface, if I call L2 over here, the problem is the antinode is not exactly here. It is formed slightly outside. It is formed slightly outside. The reason for that is something called as the end correction. So when you have an open pipe, the antinode is not formed exactly here. It is formed slightly outside. It is formed slightly outside. This is where you get your antinode from the open pipe, from the open side of the pipe. This distance where the antinode is formed is also called as the end correction, and that end correction is 0.3 times the diameter, 0.3 times the diameter of the pipe. So that correction has to be used to actually find the effective length of the pipe. If you remember over here, I had put length effective. That means it's not the actual length which you measure, you have to also take into account the end correction. you have to also take into account the end correction. So my dear warriors, over here you will see that there will be some end correction E over here, there will be some end correction E over here. So technically I can say length 1 plus E is lambda by 4. Here length 2 plus E is 3 lambda by 4. Subtracting the 2, this minus this, what will I get? What will I get? Okay, just take bigger number minus the smaller number. Just take the bigger number minus the smaller number. If I subtract the 2, so subtracting, what will I get? Observe carefully. Observe carefully. L2 minus L1, I'll get L2 minus L1. E and E will cancel, and here I'll get 3 lambda by 4 minus lambda by 4, which is 2 lambda by 4, which is just lambda by 2. But lambda is nothing but speed by f, speed by frequency. So that is nothing but L2 minus L1. So rearranging, I'll get f is v by 2 times L2 minus L1. This formula is also very useful to find the frequency of the tuning fork if speed of sound is given and the two lengths for first harmonic and third harmonic. Consecutive harmonics, first and third are the immediate harmonics. Consecutive harmonics are given to you, this length and that length. Without knowing the end correction, you can find the frequency. You can find the frequency. Is that right, everyone? Okay, so one formula which you must know is this formula in general. Okay, but here you need to know the end correction, and the other formula is this one, where you know the first harmonic and third harmonic lengths. End correction gets cancelled when you subtract, and we derived this. So you should know that. End correction is 0.3 times the diameter. This is also one thing which you must know. Let's have a look. A tuning fork of some frequency tolerance 1% is used in resonance column method. The first and the second resonance are measured at this and this length. Find the maximum permissible error of speed of sound. Okay, so we already have seen the formula for frequency, which is V by 2 times of L2 minus L1. Formula for frequency is V by 2 times of L2 minus L1. So therefore, speed of sound will be 2 times F times L2 minus L1. Now this L2 minus L1, let me call it as the length difference as X. Let me call it as the length difference, which is X. So therefore, think about it. When I try to find the relative percentage error in the speed of sound, when I try to find the percentage error in the speed of sound, this number 2 will not make any difference. Find the relative error in frequency. Find the relative error in frequency, and also just add to it the relative error in that term X. Relative error in the term X, multiply by 100, you will get it percentage. Okay, so now do I know the frequency percentage error? Yes, the percentage error in the frequency is just 1%. How much is the percentage error in the difference of the lengths? That is the tricky part. That is the tricky part. Let me just create a duplicate of this. Okay. Okay. And tell you how much is delta X by X. Observe carefully. It's given the lengths are 24 and 74.0. Do you see the decimal places is still first decimal? So that means the least count is 0.1 centimeter till first decimal accuracy is there. So the least count or the error is 0.1 centimeter. Very good. Now, when I try to find X, which is nothing but L2 minus L1, meaning 74 minus 24. 74 minus 24. That's going to be 50 centimeters. That will be what X is. But remember, the errors are always added. The errors are always added, even if you are subtracting. So delta X will be 0.1 plus 0.1, which is 0.2, which is 0.2 centimeters. That will be the error in the difference of the lengths. Errors are always added. So when I find delta X by X, which will be 0.2 divided by 50, and then I try to find percentage, that means multiply by 100. So 50, 100 becomes 2. So it will become 0.2 into 2, which is 0.4%. 0.4%. That is the relative error in the difference of the lengths, percentage wise. So put that 0.4 over here. Put that 0.4 over here. Hence, the final answer that you will get is 1.4%. Many students make a mistake here. They think that the error will still remain 0.1. That is the most common mistake, and you will get a completely wrong answer. Understood? Clear? So hence the answer for this is 1.4%. Moving on to the next question coming up on your screen. In a resonance tube experiment to determine the speed of sound in air, a pipe of diameter 5 centimeters is used. The air column in the pipe resonates with a frequency 500 when the minimum length of the air column is 15.5. Find the speed of the sound in the air at room temperature. This word minimum length is 15.5. You know what does this mean? Why the minimum length is given? Look at this diagram. The first resonance, first harmonic happens in this manner. So that minimum length L1 is what is given to you. This L1 is given. This is not third harmonic or fifth harmonic which is given. The first time the resonance occurs is for the first harmonic when lambda by 4 is the length of the standing wave which is produced. Lambda by 4, which is the length of the standing wave which is produced. Oh, so this data, because it is given to me as minimum length, that means it is first harmonic. It is first harmonic. Okay, question is find the speed of sound in air. We know the formula for frequency is odd times V by 4 length effective. So therefore, V will be F into 4 into length effective divided by the odd number. 4 is 4. Frequency of the tuning fork is given to be 500. Great. Length I don't know. Odd number is 1 because first harmonic. Now what is that length effective? Well, that length effective is the actual length plus the end correction. What is the actual length? It is 15.5 centimeters plus 0.3 times the diameter. Diameter is also given. 0.3 times the diameter, everything in centimeter. So this will become 1.5 plus 15.5. That's 17 centimeter or 17 into 10 to the power minus 2 meters. So the effective length becomes 17 into 10 to the power minus 2. Solve this and see how much do you get. Solve this and see how much do you get, my dear students. Come on. 4 5s are 20, and then into 17, that's 34, and with 1 0, so 340 meters per second. 340 is option C for Captain Shreyas. C is Captain for Captain Shreyas. Very nice. Is that understood, everyone? What a brilliant question it is. Okay? You have used end correction also, and we have used harmonics knowledge also by using this data. This word was very important. Minimum length means first harmonic. Okay. Now specific heat capacity type of questions, specific heat capacity experiment. In this kind of experiment, what happens is basically you have one hot body, one cold body. You mix that hot and the cold body and let them achieve an equilibrium after some time. You will see that whatever heat is lost by the hot body will be the heat which is gained by the cold body till thermal equilibrium is achieved. This is basically your principle of calorimetry. Principle of calorimeter. There will be one thing which will be losing energy, one thing which will be gaining energy, and their loss and their gain will be equal because the heat can't go anywhere outside to the surroundings, or nor can it come inside. So you can see over here, this is a calorimeter, which is basically an insulating device. It prevents any heat flow inside and outside. There is a thermometer to see what is the temperature. If the temperature is changing, that means it has not yet reached equilibrium. Once the temperature stabilizes, that's when it has reached thermal equilibrium. Okay, and here is where you also have a stirrer, so that you allow the liquids or the solid, the whatever particles are there, to mix till they exchange heat enough and attain their thermal equilibrium state. In these kind of questions, usually the formulas for heat that you might need is Ms delta T, where S is specific heat capacity, and other formula which you might need is Ml, which is where L is nothing but your latent heat. L is nothing but your latent heat. L is nothing but your latent heat. This is also sometimes very, very useful. So my dear warriors, remember these two formulas for heat absorbed or heat released. M is mass, L is the latent heat. M is mass, this is specific heat, this is change in the temperature. These two formulas might be used for your heat lost and heat gained calculations. I will show you a question on this. It's nothing different. You don't have to be scared about calorimeter question. These kind of questions can come. There is a metal block of some mass, some temperature, is in this much water at 25. Final temperature is this much. Heat capacity of water is this much. Determine the specific heat capacity of the metal block. Okay, let's try to solve this. Thank you so much, Sunita. Thank you. And those of you who are joining a little bit late, it's still okay. You can watch from any experiment. Whatever experiments you have missed, you can watch it later on. So for this particular thing, identify who is the cold object. The cold object is 150 grams of water at 25 degrees Celsius. The hot object is this metal block at 150 degrees Celsius. The equilibrium temperature is 35. That's it. So I can say the heat gained will be equal to the heat which is lost by the hot body. Heat lost by the hot body, mass of the hot body 250 grams, into specific heat capacity, I don't know that, into delta T, final and initial, these are the values. So the change in the temperature is 150 minus 35. Don't put 35 minus 150, okay, because you have to put only positive values. We are talking about heat lost, okay, not the heat exchange net. So don't put it with sign, it will be a positive value. Heat gained, who will gain the heat? The cold body. How much is the mass? 150 grams. How much is the specific heat capacity of water? It is 4.18 joules per gram degree Celsius. Change in the temperature, from 25 it went to 35. So 35 minus 25. Everything you know over here, the only thing you don't know is S. Solve it and find the value of S. I think it should come out close to 0.2 joules per gram degree centigrade. 0.2 joules per gram degree centigrade. That's what you will get after solving. It's nothing but a calculative question after this. Cool? Yep. Shall we go ahead, my dear students, now to the next one, the next experiment coming up on your screen. Next experiment coming up on your screen. Okay. Next experiment is meter bridge. Meter bridge is used to find unknown resistance. It is based on the principle of Wheatstone's method of balancing resistors or capacitors. Wheatstone's method of balancing resistors or capacitors. So what happens in Wheatstone? Is basically you have one resistor, another resistor, one more resistor, another resistor. Okay. Maybe some current is coming in from here, going out from here. This is R1, this is R2, this is R3, this is R4. Then if you put up a voltmeter, or ammeter in between, it might show some reading, but if the reading is 0, then it is called as null deflection. And then this bridge, this is called as a bridge. This bridge is said to be balanced. And when that bridge is balanced, then R1 by R2 will be R3 by R4. This is the concept of Wheatstone's bridge which is balanced. If it is unbalanced, then it might show some reading. When it is balanced, then it will not show any reading in the voltmeter or the galvanometer. Now, this same logic is used over here. You can see there is one resistor here. There is some unknown resistance here. There is some resistive wire here. You can see a voltmeter or a galvanometer is connected between 2 points. Actually, this is one resistor. This is another resistor. This is another resistor. And this is another resistor. And you can also see a voltmeter or a galvanometer connecting these 2 points. So this is also a Wheatstone's bridge, just like over here. If I know R3 by R4, the ratio, then if R1 is known, I can find R2. If R2 is known, I can find R1. So if I know this ratio, R3 by R4, I can find R1 if I know R2. I can find R2 if I know R1. Now this ratio of R3 by R4, if you notice over here, R3 by R4 will be proportional to the length. This resistance as a whole, whatever the resistance is, it is spread across 100 centimeters. So a part of it is R3, a part of it is R4. So since resistance is proportional to the length, this R3 by R4 will be nothing but L3, or basically L by, or L, I can just call it some, let's say this I call it as L3, let's say I call this as L4. I can just say it is nothing but L3 by L4 because the resistance is directly proportional to the length. So measuring these lengths, I can easily get the answer. So over here, R1 is basically R. R1 is basically R. R2 is basically that unknown resistance X. Similarly, L3 and L4, what are they? L3 is this length. L3 is this length. And L4 is basically this length. This is known, this is known, this is known. You can find out this. That's all the concept is in meter bridge. This galvanometer is first tried and tested here. If it shows reading, then you move this point somewhere else. If it still shows reading, then again you move the point. If it still shows reading, again move the point. If it shows 0, then you stop and only then measure it. That is called as your null deflection length. Null deflection length, because there is no deflection only in the galvanometer. That's the idea behind it. Is that okay? Very good. Let's have a look at some questions. In a meter bridge, when the resistance in the left gap is 2 ohms, an unknown resistance is there in the right gap. Okay. So in the left gap, if the resistance is 2 ohms, unknown resistance is there in the right gap. And the meter bridge is at 40 centimeters from the 0 end. That means this is 40 centimeters. Because it is 1 meter is 100 centimeters. Naturally, the remaining part will be 60 centimeters. That's when you get null deflection over here. That's the first criteria. That's the first piece of information. From that, 2 by x will be 40 by 60. 40 by 60 is 2 by 3. So 2 cancels. So x will be 3 ohms. The unknown resistance is how much? 3 ohms. But that's not the question. The question is only something else. On shunting the unknown resistance with 2 ohms, the shift of the balance point on the bridge is. Meaning, you take this 2 ohms as it is. The unknown resistance which was 3 ohms. Unknown resistance which was 3 ohms. You shunt it. Shunt it means put another resistor in parallel. You put another resistor in parallel. That parallel resistance is itself 2 ohms. Then you will get a new length. Then you might get a new length. Maybe I will call it this as x. So the remaining will be 100 minus x. Is that right? When you balance it, when you again balance it, you might get a new length. Okay. So what is that change in the length? We can find it out. For that, first figure out how much is this effective resistance since they are in parallel. Shunt means parallel. Remember that. Shunt means parallel. So the parallel resistance will be R1 R2 upon R1 plus R2. 2 3s are 6. 6 by 5 ohms. 6 by 5 ohms. So hence over here I can say x by 100, or I can say x by 100 minus x, this by this will be this by this, so 2 by 6 by 5, 2 by 6 by 5. Now it's just simple math. 2 5s are 10, and in fact I can write it like this, 5 by 3 will be x by 100 minus x. Solve this, cross multiply, so 3x will be 500 minus 5x, so 8x will be 500, so x will be 500 divided by 8, 500 divided by 8, which is how many centimeters, my dear warriors? Which is how many? Yes, some of you already posted it. Very nice. 62.5. Very good. See this. Very nice. 62.5 centimeters. Very nice. But the question is not even to find that. The question is how much is the shift? Read the question carefully, my dear students. Find the shift. So the shift is 62.5 minus original length was 40 minus 40, which is 22.5 centimeters, which is 22.5 centimeters. Is that clear? Is that clear, my dear students? Very good. Moving on to the next one coming up on your screen. Resistance using Ohm's law. This is one of the easiest thing. I mean, you have done this back in the day in your 9th or 10th grade, where you take a battery, you take a switch, you use an ammeter, you use a voltmeter across a resistor, measure the voltage across the resistor, find the current through the resistor, and then plot a graph, and then verify Ohm's law. Very, very straightforward. Very, very straightforward. So in this kind of thing, we'll see that the voltage will be directly proportional to the current, or voltage will be I into R. That's the only formula which is needed. Nothing great about it. There is a rheostat. When the word rheostat is used, what it actually means is a variable resistance. Variable resistance. Why do I need that? Because when I add or subtract resistances, then the circuit characteristic changes, more or less current will pass. So when the current changes, voltage will also change. And that's exactly what you have to do. You will, have voltage on one side, current on one side, and then you will set it at one particular position, and then you will see what is the current and what is the voltage. Then you will remove it and put it on some other side. You will change the resistance. You will see the new voltage will be there, new current will be there. Again change the resistance, new voltage, new current will be there. You slowly try to join all these points with a line. It should pass through the origin. If it doesn't pass, make it pass. It has to. That's how you show voltage is proportional to current, and from the slope you can measure the resistance. That's all. So you'll see the graph will be a straight line, whether you draw current versus voltage or voltage versus current, doesn't matter. So just to give you some example, question will be find the resistance, and you can have two kinds of graph. One is current versus voltage, one is voltage versus current, and let's say the graph looks something like this. This is 2, this is 6, this is 2, this is 6. Example. In each case, can you find what is the resistance? Alright. So all you need to do is check the slope, or just put V is equal to IR. Nothing is there in this problem. When the voltage is 2, the current is basically 6. So R will be 1 by 3 of ohm, as straightforward as that. And over here, again using V is equal to IR, when the voltage is 6, the current is 2. So therefore, R will be 3 ohm. So understand, you need to check whether it is current versus voltage or voltage versus current, or else you might get exactly different answers, reciprocals of them. Right? Awesome. Yeah, it is kind of summaries of all the chapters, and if you know the chapter, you can do it very easily. Right. Moving on to the next one. This one. Half deflection method. Some of you might know it, some of you might not have done this, but Hopefully this was done in your college or school. In this half deflection method, what happens is, the idea is to find the resistance of a galvanometer and something called as the figure of merit. Figure of merit. Any galvanometer is nothing but a resistance, because there is a coil inside it. That coil has some resistance, that is called as the resistance of the galvanometer. There is also something called as figure of merit, meaning it's the quantity of current which is required to move it by one division. Remember, the galvanometer scale has some divisions on it. If previously the arrow mark was here, now you want to shift it, the needle, to here. So to create this shift, how much extra current you need? So that is called as your figure of merit. That is called as your figure of merit. So from one division to the next division, to change the needle's position, how much more current you need, that is called as the figure of merit. Understood? Oh, clear? Oh, great. Now, in order to find that, what is done, let me explain you the setup. First, what is done is you just have one galvanometer connected to the battery with some small resistance. Can you see that? Battery is there, some resistance is there, galvanometer is there. Okay, the galvanometer will show some deflection. You note down the deflection. This theta is basically your deflection. Is that right? Everybody with me? Now you add one more resistor in parallel. This S stands for shunt or basically parallel resistance. Now you keep changing this resistance, change it. Try to use different values of resistances till the deflection here becomes theta by 2. This is basically called half deflection. Note down that resistance S. What is S? The resistance for which you get exactly half deflection. Without any parallel resistance, you get some theta deflection. Let's say it was showing 24 units. For 12 units, how much resistance you need to add? That's all. Great. Then when you get that, just find the resistance of the galvanometer using this formula. See, what is the formula? Galvanometer resistance is Rs by R minus S. R is this resistance, S is this resistance, so Rs by R minus S. If you know this formula, directly you can solve the question, else the derivation for this is very lengthy. Don't do that. Next thing, this is the figure of merit formula. This is the figure of merit formula. Figure of merit. This is resistance of galvanometer formula. EMF you should know, divided by R plus G, not S, R plus G into theta. Theta is the deflection. Theta is your deflection. Do you see that theta over here? That is that deflection which you basically get over here. This theta is your deflection which you get over here. So when you have no resistance in shunt or parallel, whatever deflection you get initially, that theta you can put over here. It can be in radians, it can be in degrees, or it can be in just divisions also. Either way. No, this is a breakless class. I don't think we'll take more time. We have already reached the 12th experiment. There are only some few more experiments which we have to discuss. So I don't think we'll need more time. Okay, lot of time. Right? Yes. All right. Cool. So let's solve a question based on this. In an experiment to determine the resistance of a galvanometer by half deflection method, the circuit EMF is 25. Half full deflection. Oh my god, I think the two words have came together. This was not half. The full deflection is 3 divisions. In one set of reading, if R is equal to 10 ohms, S is 4 ohms, then the resistance of the galvanometer is. Okay. So the resistance of the galvanometer, just use this formula. Resistance of the galvanometer. I'll just use G symbol. What is that formula? Rs by R minus S. It is Rs by R minus S. What is the resistance which is added separately? The resistance which is added separately, that is basically 10 ohms. What is the shunt resistance? Shunt resistance is this parallel resistance, that is given to be 4 ohms by 10 minus 4. So it will be 40 by 6, which is 20 by 3 ohms. That is the galvanometer resistance. We found that out. 20 by 3. Everyone? Very nice. But that's not all. We can also find the figure of merit if it was asked. Figure of merit. Figure of merit. What is the figure of merit formula? Look at this. E by R plus G theta. It is nothing but E by R plus G into your theta. What is the EMF? 25 volts. What is the resistance? 10. What is G? We calculated here, which was 20 by 3. What is theta? 3 divisions, I think. Yes, 3 divisions. 3 divisions was there, right? So now solve this. 25 by 30 plus 20 is 50. 50 by 3 into 3. 3 cancels. This will become half. So half ampere per division. That is the figure of merit. It's like your sensitivity only. It's like your sensitivity only, right? Great. Very nice. Moving on to the next one, that is finding the focal length using your displacement method. This is what is there in your syllabus, where you have an object like a candle or a light source, you have a lens, and on the other side you have a screen where you measure or where you get the image of this particular source or the object. You adjust the lens in such a way that you get the image on the screen. You adjust the lens in such a way where you get the image on the screen. Guess what? There is not one, but there are 2 positions for which you get images on the screen. Once here, once there. So you keep moving the convex lens till you see the image. Keep moving it till you again see the image. So you will see 2 times. You will see the image 2 times, and that's what will help you find the focal length of the convex lens. It is called as the displacement method. It is called as the displacement method because once the lens position is here, so you are displacing the lens from here to here, which is let's say x, that is why you are calling it as the displacement method. If you know the total distance between the source and the screen, let's say it is capital D, then the focal length is given by d square minus x square by 4d. d square minus x square by 4d. That is the answer. That is the answer. Is that okay? All right. All right. Very good. One more thing which you should also know here is that the images that you get on the screen, if you measure the image heights, height of the image in the first case multiplied by height of the image in the second case, if you multiply it and then put it inside the root, you will get the height of the actual object. So the root of height of image 1, height of image 2 in both the cases will be the height of the object. This is also a very important formula. This is also a very, very important formula. Keep these things in mind. So let's have a look at some questions based on this. An object and a screen are fixed at a distance d. A converging lens is placed. A real image is formed on the screen for 2 positions. Their separation is how much? Basically, x is asked. If you know the formula, directly you will get the answer. D square minus x square by 4d. Shift it over here. So 4df is d square minus x square. So x square will be d square minus 4df. Taking d common, it will become d into d minus 4f. So x will be root of d into d minus 4f. So d into d minus 4f, and you will see that is option number B. It is option number B. Straight questions can come, direct questions. Yes, you can use sunlight and also find the focal length. There is no harm in that. Okay. Now over here again one more question. You can see D is given, X is given, and the question is what is the focal length? So very direct, very simple questions you will get on these particular arrangements. So my dear warriors, again the formula that you have to use, is F is D square minus X square by 4D. D is 75, X is 25, 4 into D, which is 75. So take 25 common over here. So 25 square, 25 3s are 75. So 3 square minus 1 square, whole thing divided by 4 into 75. Solve this because this is 25 into 25 into 3 square is 9, 9 minus 1 is 8, divided by 4 into 75. 25 goes with 75, 3 times 4 goes with 8, 2 times. So you should get this as 50 by 3. Yes, 50 by 3 centimeters, correct. That is the answer. So 50 by 3 centimeters. Understood? Clear? Direct questions can come on this. If you get these questions, you should be very happy. Directly you will solve it. So experimental physics is all about knowing the formulas, knowing the concepts, and it is always better you know the chapter from before. If you don't know the chapter from before, it is going to be little difficult. Prism concept again. Over here in practical physics, the next experiment, the plot of the angle of deviation versus the angle of incidence of a triangular prism. A very, very standard graph where you let the light enter at some angle, it refracts 2 times, and it finally deviates by some angle, and you plot that deviation for different angles of incidence. That graph ends up looking like this. For different angles of incidence, the deviation looks like a curve which is symmetric, and there is an angle when the deviation is minimum. There is an angle of incidence when the angle of deviation inside the prism is the least. So what is the meaning of this deviation? The light was going like this, but because it bent, it ended up going like this. So you can see this is the angle by which the light has deviated. This is the angle by which the light has been deviated. Is that right? So if you plot that delta versus incidence, you will get a symmetric curve with a minimum at a particular angle. Now it so happens that for minimum deviation, do you see this angle of incidence? Do you see this angle at which it emerges out? These both happen to be equal. So you can see that for delta minimum, angle of incidence is angle of emergence. Number 1. Angle of incidence is angle of emergence. Not just that. Do you see the internal angles here? If these two are equal, naturally these two will also be equal. These are the internal angles of refraction. So you will also see R will be equal to R prime. In fact, they both will be A by 2 because R plus R prime is actually A. R plus R prime is the angle of prism. Because R and R prime both are equal, so R plus R will be A, or 2R will be A. That means R will be A by 2. That's the reason why I said R, R prime both will be equal and it will be A by 2. Is that okay? That is another thing which you must know. Not just that, you should also know in general deviation is incident angle plus emergent angle minus the angle of the prism. All these are standard formulas. Deviation is incident plus emergent minus A. In case of minimum deviation, I and E will be equal. Also at minimum deviation, you get the refractive index to be sine of angle of prism plus minimum deviation by 2, whole thing divided by sine of A by 2. That is what you get the refractive index to be. I hope this is very clear. Yes, awesome. Now going back over here, you can also use Snell's law. at this and this interface. So mu, refractive index, is sine of angle of incidence in air, which is I. In air it is I. Inside glass it is R. So sine of R, which I can also write sine of angle of incidence in air, which is E, upon sine of angle of incidence in the glass, which is R prime, sine of R. This is also applicable, your Snell's law. Your Snell's law is also applicable. These are the most important formulas for this particular experiment. If you know these formulas, then it becomes very, very easy. Look at this. For an equilateral prism, the deviation is same for 55 and 35. The minimum deviation is how much? Refractive index is how much? Angle of incidence for minimum deviation is how much? Graph is how much? Okay, let's try to do this. First of all, if I draw the graph, it will be very easy for me to understand this. This is angle of incidence. This is your deviation. The deviation is same for two angles. If you look at this particular graph, generally you will get the same deviation for two angles. Whatever is their left side is also their right side. It is a symmetric graph about this line. Whatever is their left is also their right. So there are two angles for which you are getting the same deviation. That's what it says. So if I happen to draw this graph which is like this, I am getting the same deviation for two angles. What is it? 35 degrees and 55 degrees. So think about it. When will minimum deviation occur? When will minimum deviation occur? Exactly at the midpoint of these two, because it is symmetric. So what will be that value? It will be 35 plus 55 divided by 2. 35 plus 55 divided by 2, which is nothing but 90 by 2, which is nothing but 45 degrees. So this will be 45 degrees. That is the angle of incidence. And for minimum deviation, we know I is equal to E. Therefore, I is equal to E is equal to 45 degrees. Is that right, everyone? Everybody with me? So did we find the minimum deviation? Yes, we can find that minimum deviation using some refractive index formula. I think that refractive index needs to be given, or minimum deviation needs to be given. Without that, I think one of them is missing. Without that, we will not be able to find it. Okay, I think one of them is missing over there. I think minimum deviation needs to be given over here. Okay, let me just put up over here. Let's say minimum deviation, let's assume something. Example is 30 degrees. This needs to be given. Without that, we will not be able to, because nothing else is given over here. So all right. So with this, I think we can now find the refractive index, because mu is sine of A plus minimum deviation by 2 upon sine of A by 2. We can use that. Yes, we can use that, right? And no, minimum deviation is not 45. Angle of incidence is 45. Be careful. Mu I do not know. Sine of A, angle of prism, because it is equilateral prism, angle of prism is 60 degree. So this will be 60 plus minimum deviation is 30 divided by 2, whole thing divided by sine of A which is nothing but 60 degree by 2. So 60 plus 30, 90, 90 by 2, 45. So it will be sine 45 by sine of 30, which is 1 by root 2 by 1 by 2, which is root 2. So I just got refractive index as root 2. We just got refractive index as root 2. Then what else is remaining? What is that angle of incidence for minimum deviation? That is also done. Very nice. And we drew the graph also. That is also done. Yes. So you have done everything in this. You have done everything in this. Clear, my dear students? Clear, my dear students? Very nice. Very nice. Great. Okay. Shall we move ahead now? Shall we move ahead? All right. Let's see. The next one, refractive index of a glass slab using a traveling microscope. This is one of the easy ones, one of the easy experiments. Very nice. Everybody wrote the final answer for the previous question. Here we know that when you look inside a swimming pool, the surface of the pool appears closer. That is the concept of apparent depth or apparent height. That happens because of refraction phenomena. Now, you might have also seen this. If you take a glass slab and place it in front of something, that surface appears little bit closer. So over here, what happens is that, my dear warriors, you, let's say for example, are viewing a point through a microscope. You're viewing a point through a microscope. There is a point or a dot or a particle through a microscope. You are seeing it. Now, if by chance you put a glass slab in front of it, then what will happen? That particle, that point which is marked, will no longer be visible there. It will appear little bit closer. It will shift by some amount. Because of which, this microscope which was there, you will have to move it little bit up exactly by the amount which it has shifted. Exactly by the amount which it has shifted to focus it again. Earlier, the microscope was, making sure whatever rays come over here, they are focusing at the proper point. But now, if you use a glass slab, then that point will appear at some other place. So to focus it again without disturbing it, you just have to move it little bit up so that you accommodate for it. So that's the whole concept of measuring the refractive index using a microscope for a glass slab. We know that if an object is over here at a depth of let's say t being the thickness of the slab, t being the thickness of the slab, when seen from here, that object's position will appear here. This is called as the apparent depth. This is called as the apparent depth. This is where the image of the object is formed. The distance by which the object shifts to form that image, that is delta x, which is also called as the shift, in the position. So when you are seeing from here, the object which is on the other side will appear a little bit closer to you. That apparent height formula is actual depth, in this case actual depth divided by refractive index. In this case, the actual depth is t. You can see it is t centimeters or t meters inside. Refractive index is mu. Hence, when I find that shift, delta x, which will be total thickness minus the h apparent, will be t minus t by mu. Taking t common, it will be 1 minus 1 by mu, whole thing into t. That is your shift which is produced. So if you are earlier focusing on O directly, you will have to shift by that much amount to focus on it properly again. So the shift, the apparent shift produced by the slab is same as the distance by which the microscope has to be moved to focus again on that particular image properly. Okay, everyone, let's solve some questions. Look at this. Everybody concentrate now. It's clearly mentioned a microscope is focusing at a point. Okay, marked on the piece of paper. Now you take a glass slab, glass slab, okay, you take a glass slab of thickness 12 centimeters. So because of which what will happen, this microscope will have to be moved little bit. It has to be moved little bit by delta x. Question is, if that microscope shift distance, sorry, is given by 4 centimeters. You have shifted the microscope by 4 centimeters. Question is, what is the refractive index of the glass slab? Question is, what is the refractive index of the glass slab? Because now the marking will also appear somewhere else on that piece of paper. On that piece of paper, right? It will appear somewhere else only. It will appear slightly at a different place. So here just use the shift formula, you will get the answer. Delta x is thickness into 1 minus 1 by mu. Delta x is 4, thickness is 12, 1 minus 1 by mu. So this will become 1 by 3 because 4 by 12 is 1 by 3. 1 minus 1 by mu. So 1 by mu is 1 minus 1 by 3, which is nothing but 2 by 3. Reverse it, reciprocal will be 3 by 2. So refractive index is 1.5. So 1.5 is the refractive index. Clear? How to solve this? Very nice, my dear students. Awesomeness. Next one on p-n junction. Next one is on p-n junction, where you draw or understand the characteristics of the p-n junction diode in the forward and the reverse bias. Remember, a p-n junction is where on one side you dope it with a pentavalent impurity and the other side you dope it with a trivalent impurity, so to make one side electron excess, one side hole is in excess. So the p side has holes in excess. The p side has more number of holes than the number of electrons, and the n side has more electrons than the number of holes, right? And then you join them together to make it into a p-n junction, and when that junction is formed, there are two things which happen. There is a diffusion current and drift current. Both things happen. Remember that. Both things happen. So when you have a p-n junction, you will see that the electrons from the n go towards the p. And the holes from here go towards this side, because of which you will see that there is a diffusion current which is set up this way. Diffusion current set up from p to n. If negative charges go here, positive charges go here, current's direction is the flow of the positive charges. At the same time, you also have another current in that potential barrier which is created. That happens to go from exactly n to p. This is called as the drift current. When there is no bias, then the diffusion current is exactly equal to the drift current. Hence, the net current is a 0. When there is no bias, both the currents are equal and opposite, and the net current is basically 0. Keep this in mind. Okay, I hope you are remembering all these things. So when you put it in forward bias, what happens? Forward bias means P is connected to positive, P for positive, N for negative, that is forward. Then you will see that the diffusion current is going to exceed the drift current. You are going to see P is positive, P is connected to positive, N is connected to negative. More current will go exactly in the direction of the bias. So you will see that the diffusion current grows, whereas the drift current stays as it is. So because of which you will see that there is a large net current over here in this direction. You will see the diode now allows the current to flow, but it does not allow immediately. when you slowly increase the voltage which is applied across P and N, when you slowly increase the voltage across P and N, first the current does not increase so much, it increases by a marginal amount. After a point it shoots up. Why does that happen? Is because there is a barrier. There is a barrier which is created. There is a barrier which is created. So when the voltage is slowly increased, that barrier becomes smaller. The barrier potential, the barrier becomes smaller and smaller as the voltage is increased. There is a barrier which is created which prevents the flow of the holes and the electrons. So after a certain voltage, often called as the knee voltage, you will see the barrier is broken. The barrier is broken. And then after this, if more voltage is applied, then you will get a large current. Then you will get a good flow of current. This is very, very important. Okay? In the exact opposite scenario, where you connect it in reverse bias, means P to the negative, N to the positive, P to the negative, N to the positive, you will see that the diffusion current does not grow. In fact, the diffusion current becomes smaller. The diffusion current becomes smaller, and the drift current, it stays as it is. Nothing happens to it. Drift current stays as it is. Okay, the drift current stays as it is. That's the reason why you will see that there is a net current which is in the drift direction, not in that direction, in the opposite direction. Remember, in forward bias it was from positive to negative, P to N. In reverse bias it is from N to P. All right, it is going like this. So there is a small net current. Often this current is so small, it is also called as the leakage current. It is also called as a leakage current. It is also called as a leakage current. So I can say it stops current. It stops. Leakage is very small. This leakage is very, very small. So it stops the current in the other direction. That is why it is called as a diode, because in one direction it allows the current to flow in large amounts, but in the other direction, when it is biased, it does not allow too much current. So it is like a one-way traffic of current. That's why it is a diode. If you draw the graph of voltage versus current, observe this carefully. This is voltage, this is current. When you are on the right hand side, it is forward bias because voltages are positive in number. On this side, you will see voltages are negative. That's why it is a reverse bias. That's why it is a reverse bias. Now notice what happens when the voltage is increased. The current increases over here in case of forward bias, but not so much till it reaches something called as the knee voltage. Till it reaches something called as the knee voltage. Look at it, exactly what I had mentioned here, where the barrier is broken. After the barrier is broken, there is a large current, exactly what you would expect. You can see suddenly the current shoots up. Suddenly the current shoots up. Everybody with me? Very nice. Awesomeness. So this is very, very important, and you should remember what is the knee voltage for germanium and silicon. Okay, I think it has been, no, it's fine. So 0.7 for silicon and 0.3 for germanium. 0.7 for silicon and 0.3 volts for germanium. After these voltages, the current increases by a good amount. In the reverse bias, notice how the current is small for a long time. This current is very, very small in the reverse bias. That is why it is called as leakage current. Notice how the currents are in microamperes. Micro is very, very small current. Micro is very, very small current. And there comes a voltage after which it does not grow, breakdown occurs. That is called as the Zener breakdown. After this, no matter what you try to do, the voltage can't be increased. The current changes, yes, but the voltage does not change. So you maintain that voltage. That is actually the application which is used for Zener diode in reverse bias. So in reverse bias, it happens, but in forward bias, you don't get a saturation like this. No. In reverse bias, you get a saturation over here where you can't further increase the voltage beyond this point. Current can increase, that's okay, but voltages can't be changed. So if I use this property and I use the diode in this region, what I will ensure is the voltage never grows beyond a point. That is what is the concept which is used in Zener diode. We connect it in the reverse bias and you use it in the breakdown region, so the voltage remains the same and it is going to act like a regulator, meaning it does not allow the voltage fluctuations to happen. So this is the current voltage characteristics of a PN junction diode. You should know it in and out. You should know it in and out. This is a symbol of a diode. This arrow mark tells you in which direction it allows the current. In this direction, it will block the current. It will block the current. Okay? Keep all these things in mind. Cool. So let's have a look at some questions. The reading of the ammeter of a silicon diode in the given circuit is, it's a silicon diode. Silicon, remember, will have a knee voltage of 0.7 volts, of 0.7 volts. Okay, so this will be 0.7 volts over here. So out of 3 volts, 0.7 volts is dropped. How much will be remaining? Think about it. How much will be remaining? 2.3. 2.3 volts will be remaining over here. Everybody with me? 2.3 volts will be remaining here. Question is, what is the current or the ammeter reading? Well, if you want to find the current, use V is equal to IR for the resistance. Voltage is 2.3, current I don't know, resistance is nothing but 200 ohm. So I will be 2.3 divided by 200, which is also 23 divided by 2 into 1 by 1000, the decimal I have shifted, which is 11.5. 1 by 1000, I can write it as milliamperes. 11.5 milliamperes. Yes, that is C for Captain Shreyas. That is C for Captain Shreyas. Yeah, negative y-axis, is it microamperes? You can write it in a different scale. Okay, you can write it in a different scale also. But if you write it in the same units, milliamperes and milliamperes, here the currents will be large. Here it will be so small that you will hardly see it away from the minus x-axis. It will almost be touching it. Here it is highly exaggerated. It is very, very close to the negative x-axis. Next question. So for that Zener diode, guys, let's have a look at what Zener diode does. Like I said, Zener diode is used to regulate the voltage. To regulate the voltage. Okay. It is operated in the reverse bias. It is operated in the region of breakdown, reverse bias breakdown voltage, reverse down bias breakdown voltage. Meaning, if I have a Zener diode, the symbol for a Zener, it's a normal diode, it's just that it is doped really heavily, that's all. That's the symbol. Normal diode does not have these two lines. When you draw these two lines, it becomes a Zener diode. Now, no matter how much voltage you apply to this, apply to this, if you measure the voltage across the Zener diode, if this is your output voltage, and maybe, you know, you have applied some input voltage. If I tell you the breakdown, occurs at 10 volts, then if you plot a table of the input versus the output, if the input voltage is 12 volts, the voltage across the Zener diode will still be 10 volts. If the input voltage is 15 volts, then also it will be 10 volts. If it is 20 volts, then also it will be 10. If it is 21 volts, then also it will be 10 volts. Always it remains 10 volts. The only problem happens if it goes below 10 volts. Say for example, it is 9 volts, then this won't be 10. This might be, I don't know, maybe 8 volts or something. Just giving an example. Okay. So it will not be, but point is it will not be 10 volts. So you have to ensure that the input voltage is above the breakdown voltage. Then the voltage across the Zener diode, remember, will remain constant. Use this graph. Use this graph. Where did it go? In the reverse bias, no matter what you try to do, across the Zener diode, the voltage can't change. The voltage can't change. It has to remain same. So you might be wondering, sir, what happens to the remaining voltage? What happens to the remaining voltage? Well, if I write on the other side, the voltage across the resistance, the difference will be given over here. So 12 minus 10, 2 volts. So you will get 2 volts drop here. 15 minus 10, 5 volts drop here. So 10 plus 2, 10 volts here, 2 volts here. 15 here, 10 over here, 5 over here, together 15. If this is totally 10 to 20, then 10 and 10 volts. 21 means 10 and 11 volts. So 10 and 11, 10 and 10, 10 and 5, 10 and 2. Always this will be 10. The remaining voltage is dropped across some other resistor or other device. So that's how it is able to regulate the voltage. You can see that. That's how it is able to regulate the voltage. It's maintaining the voltage. Okay, that's the logic behind it. Cool. Let's have a look at one question on the Zener diode coming up on your screen. Question is, find the currents in I, IZ and IL. Find the currents in I, IZ and IL. Okay, let's have a look at it. How do we do that? Well, first of all, this is Zener diode whose breakdown is 10 volts. That is given to me. So this 10 volts is not only across this diode, because this resistor is in parallel with this. This resistor is in parallel with this. So these 2 points are at the same voltage. These 2 points are at the same voltage. So hence the voltage difference between them will be 10 volts. Whether you take these 2 points for reference, they are at the same voltage, and even these 2 points are still at same voltage. So the difference between this and this is going to be 10 volts, because this is a Zener diode operated at reverse bias. So it will ensure it will be in the breakdown region only. So out of 60 volts which was given as input, 10 volts is across the Zener diode. Naturally, my dear students, the remaining voltage, how much? Remaining voltage will be how much? 60 minus 10. 60 minus 10, which is 50 volts, will be across the 4 kilo ohm. Will be across the 4 kilo ohm. Correct? Yes or no, my dear students? Very nice. So using V is equal to IR, voltage is 50, current is I, resistance is 4 kilo, 4 into 10 to the power 3. So current I over here will be 50 by 4, which is 25 by 2, which is 12.5, but this will be milliamperes. 12.5 milliamperes. I can see option C and option D over here, which has 12.5, 12.5. So either it is this or it is this. Let's check it out. Yes, it is one of them only. Other 2 options got eliminated. At least 50-50 probability we got. Okay. Now the next thing. How do I find IZ and IL? Use this particular branch. This particular branch over here. In that branch, if I again use V is equal to IR, voltage across it is 10, current is IL, resistance is 2 kilo, that means 2 into 10 to the power 3. So IL will be 5 milliamperes. 10 by 2 is 5, 10 to the power minus 3 will make it milli. Oh, so it will be 5 milliamperes across IL. IL is the third quantity, so that is 5 milliamperes. Naturally it should be D, but one more thing, we'll just try to do it. One more thing, for this particular Zener diode, if I want to find IZ, what I will do is, at this junction, I'll apply Kirchhoff's current law. I'll apply Kirchhoff's current law. Look at this. Current entering in is current exiting out. So this is 12.5. IZ I don't know. IL is nothing but 5. From this IZ is nothing but 7.5 milliamperes, which is right over here. So that is option number D. Is that right, everyone? Very good. Awesomeness. So that was our last experiment, and I hope you had fun with these physics practicals. And if you did have, and you learned a lot, please put it up. And if you did not know the theory, what does it tell you? It means we'll have to go through the theory again and again. You can search on YouTube for my lectures in English. Okay, doesn't matter whether it is on JEE or NEET channel, you can watch it if you want to understand the theory. So just search for any topic. Let's say you want to learn semiconductors, just search Shreyas sir semiconductors. Okay, you want to learn sound and waves, Shreyas sir waves. You will get the videos, whether it is one shot or long lectures, you can watch it. Okay, so I want all the students who watch this lecture till the end to put it up fun, PHUN. There is a pun over there because PPP, fun with physics practicals. Okay, so very bad joke, but still. Okay, right. So thank you so much, guys. I hope you had a great time today. We had a lovely evening. I'll be sharing the PDF later on. Okay, bye bye. Hasta la vista. Captain Shreyas signing off.